This is the first section of Chapter 7, Methods in Calculus, and here we're going to look at Leibnitz's theorem and nth derivatives. So you've already come across the product rule. So if we've got, let's say y equals uv, we know that dy dx, so u and v are both going to be functions of x, is u v dash, which is dv dx, plus u dash and v, which is going to be v du dx. Okay, and we could then apply the product rule again, so we could find what the second derivative is. So if we apply the product rule a second time, then we're going to get basically this part becomes like u, this part becomes like v, u and v. Yeah, so we'll work through this one and see what we get. So it will become u, then v dash, so this is basically the second derivative here. So at the moment we're only doing this part, so we've applying the product rule on just this bit here. So we've done half the product rule. The other half of the product rule says differentiate this and leave this alone. So the second part will be du dx times by dv dx. Okay, so we've done this part. Now we apply the product rule to this part here. So that will be plus v times by d squared u over dx squared plus, and it's going to be du dx dv dx, like this. And we could keep applying it to find like the third derivative and the fourth derivative and so on. But we know maths is all about trying to find patterns. And if I just take this second derivative, for example, I've got two terms which are the same, so these two terms can go together, so I've got two lots of that. So I'll just put plus two lots of du dx times by dv dx, and then plus, let's put 2 there, v d squared u dx squared. You may be beginning to see, well, this, I've got these coefficients 1, 2, 1, and I've got sort of u and then du dx and then d squared u over dx squared. So the derivative of u seems to be going up by powers, and then the derivative of v seems to be going down by powers. So we've got the dx squared v here, and then it's just dv dx, and then it's just v. Maybe if I highlight it in some colours that may help. So we've got u, du dx, d squared u over dx squared. That's going up in powers. The coefficients are 1, 2, 1, and then we've got dv squared over dx squared, dv dx, and just v. This reminds me of the binomial expansion. And actually Leibniz's theorem says that we can use the binomial expansion, the pattern of the binomial expansion, to find these higher derivatives, third derivative, fourth derivative, without having to apply the product rule multiple times. So for example, if I wanted to work out what this d cubed y over dx cubed was, just by using the pattern. So first of all, let's work out what the coefficient would be using Pascal's triangle. So 1, 2, 1. So I know the coefficients are going to be 1, 3, 1 or 1, 3, 3, 1. We'll start with u, and if I do this, so first term is going to have u, the second term is going to have du dx, third term is going to have d squared u over dx squared, fourth term is going to have d cubed u over dx cubed. Okay, so that follows like this pattern here, the one in green. The other term is going to be start off, well, let's start at this end. So this will be v, then this will be dv dx, sorry, so dv dx, then this will be d squared v over d x squared, and then here we'll have d cubed v over dx cubed. So you can see we're just using the pattern. Then the last thing we need to do is to put in the coefficients. So 1, 3, 3, 1. And we did that without actually having to use the product rule a third time. Okay, so we'll just write this down. We can use Leibniz's theorem to calculate nth derivatives of products. So it's got to be a product. We're starting with the product rule. Yeah, what we're doing is it's like the binomial theorem or the binomial expansion, isn't it? It's a bit like that. So I suppose what we need to do is to write down mathematically exactly what this should be, and you probably won't really use this, but we want to sort of define what this is, what it looks like. So this is the rule, but as I said, if you think binomial expansion, that will help you. So this will be the sum of k equals 0 to n. So this is basically saying we're writing out a sum of terms from the 0th term to the nth term. Then we need to work out these coefficients. Now we can write this as n over k or nck, and write it as nck. So these are basically the coefficients, like the 1, 3, 3, 1 or the 1, 2, 1 coefficients. And each one of those gets times by these derivatives. So what we have is the derivative of u starting at basically the 0th derivative, like this, and then going up. Yeah, so k starts at 0, so that will just give us the u, and then k is 1, that will give us the du dx, k is 2, d squared u over dx squared, and so on. And what we need to write is the v part of the product going down in powers, so that will be written as d, and that will be n minus k here, v over, and then dx, and again n minus k. So it's a bit unwieldy. As I said, this is how we define it, but whether you use this in an exam or not, or when you're working at questions, probably not. You'll probably just think binomial expansion. The nth derivative isn't going to be very high, and you can probably use Pascal's triangle just to work out those derivatives and just use the pattern. So the u part, u, du dx, second derivative, third derivative. The v part goes the opposite way around, so v, dv dx. second derivative, third derivative, and so on. So we'll use the pattern to work out these nth derivatives of these products. So what we've got here is to use Leibnitz theorem, which is talking about to calculate the fourth derivative of y equals e to the x sine x. So it's a product, and we want to start by working out what all of these derivatives are. So u is going to be e to the x, and v is going to be sine x. And we want to go all the way up to the fourth derivative of each one of these. So du dx, this is going to be easy, e to the x, dv dx, that will be cos x. Now second derivative, so d squared u over dx squared, that will carry on to be e to the x, and d squared v over dx squared, that will be minus sine x. The third derivative here, that will still be e to the x. Then the third derivative of v, that will be minus cos x. And then lastly, the fourth derivative, that will be e to the x. And the fourth derivative of v, that will go back to sine x. So the cycles round in that pattern. And all we need to do now is to substitute it in. So the fourth derivative, d4y over dx4. Now, to work out the coefficients, I'm just going to use Pascal's triangle. Much easier. It's easy. It's only the fourth derivative. Right, so these are the coefficients that I want. 1, 4, 6, 4, 1. So I start off with u. Then, we'll write u, won't we? E to the x. So first term will be e to the x, and that gets times by the fourth derivative sine x. Okay, so I'm using this one and this one. That's a coefficient of 1 plus 4 lots of, well, that's going to be this one multiplied by this one. So one goes up, one goes down. So that'll be 4 lots of, actually it's a minus, so I'll sort that in a moment. 4e to the x times by minus cos x plus, so we're now down to this one. So it's going to be 6 lots of these two multiplied together. So plus 6 e to the x times by minus sine x plus, so it would be helpful, I suppose, to colour code this. So that was that one, then that's that one there, and then this one was in blue, wasn't it? There. So the next one is going to be this one multiplied by this, and its coefficient is going to be 4. So plus 4 lots of e to the x cos x. And then the last one, I haven't used orange, so I'll use that one. So that times by this with a coefficient of 1. So plus e to the x sine x. So we will tidy up our answer. And that'll be e to the x sine x minus 4e to the x cos x minus 6e to the x sine x plus 4e to the x cos x plus e to the x sine x. Now this can be simplified because there are some like terms here, so this will cancel out, won't it? Like that. And then all of these are all like terms, aren't they? So we've got 2 lots of e to the x sine x, take away 6 lots of e to the x sine x, just simplifies to minus 4 e to the x sine x. So you can see this is really useful for working out these higher derivatives, these nth derivatives of these products, without having to multiply or use the product rule multiple times. Okay, so we can use Leibniz's theorem to calculate the third derivative of this product here. Okay, so this we all know how to differentiate, no problem. So from core 2, you would have learned that if you differentiate cosh x, then that becomes sin x. And because we're doing nth derivatives, we're going to be differentiating at some point sin x, and that just becomes cosh x. So this is going to be useful to do this question. So let's start by listing. So u equals x cubed, du dx is going to be 3x squared. The second derivative is going to be 6x, and the third derivative, this is as far as we need to go, is going to be 6. Right, so now let's do the same with the other part of the product, which is cosh 2x. So we'll be using the that's v, we're using the chain rule, so dv dx, so that will become 2 sin 2x. We differentiate again, second derivative, so this now becomes 4 cosh 2x. Then the third and final derivative, that will be 8 sin 2x. Right, let's color code it like before. So these two will go together. Let's write down the coefficients as well. So it's going to be 1, 3, 3, 1. So those two are going to have a coefficient of 1. This second one here and the second one from the bottom here, those go together with a coefficient of 3. This one will go together with this one, and they will have a coefficient of 3. And the last derivative of u and phi will go together, and they all have a coefficient of 1. So now it's just writing them all out and seeing if there's any simplifying to do. So this third derivative is going to be x cubed times by 8 sin 2x plus 3 times 3x squared times by 4 cosh 2x plus 3 times by, so we're on the ones that are highlighted in blue, 3 times by 6x times by 2 sin 2x plus, we're on the ones in green, 6 times by cosh 2x. So I don't think there are any like terms. We'll have a look. So we'll have 8x cubed sin 2x plus, so we've got 3 times 3, 9 times by 4, which is 36. So 36x squared cosh 2x plus 3 times 6, 18 times by 2. So that's also going to be 36. So 36x sine 2x plus 6 cosh 2x. Yeah, we don't have any like terms, so that's going to be our final answer. We can't simplify it like we did the last one. So there we go, using Leibniz's theorem to work out this third derivative of that product. Okay, so given that we've got this product here, you use Leibniz's theorem to show that for n greater than 2, it becomes this. Now notice this time we've not been asked for like the third or fourth derivative, it's the nth derivative. So when we want our working, there's going to be some n's in there. So let's start with the u part of our product, which is going to be x squared, and then we'll work out the first derivative, which is 2x, the second derivative, which will be 2. Now what happens for the third derivative and higher, we'll get 0. Okay, so basically dn u over dx to the n is going to be 0 for n greater than 3. So there are not going to be any terms after that. So we're only really going to have in this nth derivative, we're going to have 1, 2, 3 terms. Anything after that, all those terms are going to be 0. Now let's look at the other part of the product, which is v, which is e to the minus x. So dv dx will be minus e to the minus x. The second derivative will be e to the x, and so on. Okay, but actually we want the derivatives almost like coming from the other direction. Yeah, it's going to be the first term that goes with this is going to be the last term down here, the one that's basically the nth derivative. So let's do that. Let's see what the nth derivative would be. So nth derivative of v now, if I put my minus sign in here, which I'd forgot, you'll notice that they're all minus e to the x, but they flip between going minus, plus, and so on. So we want a negative 1 to a power, and it needs to be the correct power so that when, for example, n is 2, it becomes positive. When n is 3, it's negative, and so on. And actually that just matches up with n. Yeah, if you do negative 1 to the power of n, you'll get the correct sign. So for example, first derivative, so n is 1. Okay, what do we get? We get negative, right? Second derivative, n is 2. So that will be negative 1 squared. That'll become positive. So this is like the nth derivative. Now we want the term before that. Let's see if we can work that one out. So what would be the derivative, which is n minus 1? And we'll need n minus 2 in a moment, but I haven't got enough space. So let's see if we can work out what the nth minus 1 derivative would be. Well, it would just be negative 1 to the power n minus 1 e to the minus x. So we're now going to start to write out this nth derivative. But unlike before where n was like 3 or 4, we could use Pascal's triangle. We're this time we're going up to like n, aren't we? So we're going to have to write these coefficients in terms of n. So we either use nc1, then nc2, and so on, or we can write it as n1, n2, and so on. Okay, so first term, what's that going to be? Well, it's going to be a coefficient of 1. Let's actually write n1, so let's write it like this, times by u. Okay, so if I were to color code it like before, this goes with this. So that will be times by -1 to the n times by e to the minus x. Okay, plus, so the next one's going to be have a coefficient of nc2 or n2 like that. That's going to be times by 2x times by, so that is these two that go together, so that one and this one. So that will be -1 to the power n minus 1 e to the minus x. And there's only going to be one more term, plus, because everything else will be 0, and that will be this one. Now that will go with the term before the n minus 1, the n minus 2 term. Now I've not written that out, but I think we can work out what that is. So this will have a coefficient of n3 or nc3. That will get times by 2, the one that's highlighted in blue, times by, so this will be -1 to the power n minus 2 times by e to the minus x. So there's no point putting plus ... at the end, because these will be the only terms in this sequence here, or this series. Now we'll see what we can do to tidy this up. So first of all, this is just going to be 1. So anything C1 is just 1. So we just have, it's going to be x squared times by this -1 to the power n e to the minus x. Now for the next one, to help us work out n2 and n3, we can use what we know about the binomial expansion. Now let's just put this down here. You'll remember, hopefully, if you've done pure 2, you'll know that we can do the binomial expansion like this when we're expanding 1 plus x to the power n. Yeah, and then we can use these, the n part, to work out the coefficients, because that's the same as like n1, n2, and so on. So this came from expanding this, so 1 plus x to the n, and well, this matches up with the n1. This is basically n2. This here is n3. And this here is n4, if we got that far. So we can use this to write these coefficients in terms of n. So when we come to the second term, n2 here, nc2 is just n. So we can write n times by 2x times by this -1 to the power n minus 1 e to the minus x, plus, and then this n3, well, that's the same as this, n times by n minus 1 over 2 factorial, n minus 1 over 2 factorial. That gets times by 2, and then times by this -1 to the n minus 2 e to the minus x. Let's put the -1 in. Now, if we have a look at what we've got here, can you see that the -1 to the power n and the e to the minus x, sorry, have been taken out as factors? So that's what we're going to do. We'll take those out as factors. Now let's highlight them. So that's going to be taken out as a factor because every term's got e to the minus x in. And also, this is going to be taken out as a factor, and that's fine there. Now, if we take it out as a factor here, we need to put a negative in front of that term. But this is the same as -1 to the power n. Yeah, so that's also going to be the same as, so that bit there, this is the same as -x to the power n, because every other power is going to give you the same value. So let's take that out. So -1 to the power n, e to the minus x. So what are we left with inside? Well, the first term is just going to get multiplied by x squared. The second term, we need a negative to account for the fact that this is one less power than this. Is going to be a negative term. And we've taken the e to the x out, so it's going to be -2nx. So -2nx. Then we go to the third term here. Now, actually what happens is that this 2 will cancel out with a 2 factorial, because 2 factorial is 2. So we've got n times by n minus 1. We don't need to put a minus sign because it's going to be the same sign as -1 to the power n, this bit here, and we've taken that as a factor. So that just leaves n times by n minus 1. So if we have a look, we actually get the expression that they want. So we can just stick the letters QED because we've proved this as required. So you should now be able to do exercise 7a, which is on pages 151 to 152. So let's just recap Leibnitz's theorem. Which basically says if we want to find the nth derivative of a product, so we're trying to find this with respect to x, then we're basically going to be saying it's like the binomial expansion where the u part, it's doing colours, so the u part goes u du dx, second derivative of u, let's get the letters right, let's go maybe to the third derivative of u, then the v part, we go from v, first derivative of v, second derivative of v, then the third derivative of v, put it here, and then we have coefficients 1, in this case 3, 3, 1, and this would be the expansion for the third derivative of a product. Yeah, and I think that's probably the most straightforward way of doing it. So you'll need to find the first, second, third, maybe fourth derivatives of the u part, the same with the v part. Just apply the binomial expansion and you'll be able to find an nth derivative of a product.